All right, let's jump right in. Welcome to day one of our premium international masterclass on modern industrial engineering. Today's explainer focuses on something literally revolutionizing how we design and run the world around us: facility planning and digital simulation. If you want to really grasp how today's top-tier smart factories actually operate behind the scenes, you are exactly where you need to be. Okay, let's look at our roadmap for this explainer. We'll start with a quick course introduction, then hit our prerequisites, Lean and Math. After that, we dive into the course syllabus covering layout planning and digital simulation. And finally, we'll wrap up with professional standards. So part one, course introduction. We are talking about transforming the smart factory era. Just picture a traditional, unplanned manufacturing floor for a second. It's usually pure chaos, right? Constant bottlenecks, wasted movement, delayed shipments. To fix that kind of mess, the global demand for experts in precision facilities, the digital twin market alone is projected to hit an incredible $259.3 billion by the year 2032. We're seeing industries from aerospace to healthcare desperately trying to digitally transform their processes, anticipate problems before they happen, and inject heavy automation. It's a massive, massive shift. Moving on to part two, prerequisites, specifically lean principles and optimization math. Look, before we can even think about digitally modeling a factory, we absolutely have to master the basics. And that starts with lean manufacturing. This is a systematic practice, deeply rooted in purpose, people, and process. Now, a lot of folks think lean is just some corporate buzzword for cutting costs. Actually, scratch that. It's not about cutting costs at all. The real goal is improving the workflow, creating significantly more value with fewer resources by relentlessly tracking down and removing steps that just don't add value. What's really fascinating here is how incredibly specific these wastes, or muda, actually are. Take a look at the difference between transport and motion, for instance. Transport is the completely unnecessary movement of goods from point A to point B. But motion? That's the wasteful movement of a person or a machine. Imagine an operator walking back and forth across a giant warehouse 50 times a day just to grab one single tool. That is motion waste, and honestly, it's exhausting. An unoptimized facility is literally sabotaging itself with these hidden wastes every single day. Whether it's idle waiting time, sitting on excess inventory, or producing things before they're needed, our job as facility planners is to hunt these down and eliminate them completely. Once we've nailed down those lean goals, we have to translate them into hard mathematics. This is exactly where linear programming enters the chat. It's a mathematical method we use to find the absolute best possible outcome. We're talking the lowest possible cost or the highest maximum profit given a strict set of limited resources. Think of it like packing a suitcase for a month-long trip, but you only have a tiny carry-on. You want to maximize the outfits you bring while minimizing the weight, right? Linear programming takes that exact same concept, applies it to an entire factory's operational strategy, and turns it into concrete calculated data. To actually make those calculations work, we rely on four core components. First, we have decision variables, the exact variables we need to figure out to reach our solution. Then, the objective function, which is just the mathematical equation representing our ultimate goal. Next up are constraints. These are the very real finite limitations on our resources, things like available time, labor, or floor space. And finally, non-negativity restrictions, simply because in the real world, you obviously can't produce a negative amount of a product. These finite constraints and linear relationships are the actual engine driving our optimization calculations. All right, part three, core syllabus. Let's talk about facility layout and planning. Now we get to see how all this builds our physical workspace. In this module, we're entirely focused on translating high-level corporate goals into physical, concrete reality. We utilize something called systematic layout planning, or SLP, to develop the absolute optimal layout. We aggressively analyze specific material flow patterns like your I, L, U, or S flows, specifically to kill off that transport waste we just talked about. And we definitely don't just sketch these out on a napkin. We use really powerful computerized layout algorithms like Craft and LDEP to fully automate and balance the production lines. Every single square foot of warehouse unitization and inventory placement gets tied directly back to the company's bottom line. Next up, part four of our core syllabus, digital simulation and twins. So, you've got a layout design, but you don't just go out and start pouring concrete. You have to validate it first. I want to pose a direct question to you. How do we test a massively complex industrial facility without spending a single dollar on construction? The answer is digital experimentation. It offers an unbelievable return on investment simply by eliminating risk. We can completely understand system performance, throughput, and equipment utilization in a completely risk-free virtual environment. We do this using industry-standard software like Arena, which runs on a brilliant 4-step framework for discrete event simulation. Step 1. Identify the problem. You have to clearly state what success actually looks like. Step 2. Model your process using robust flowchart methodologies. Step 3. Transform your business. You do this knowing you have the confidence that the changes you're implementing are mathematically validated. And step 4. Repeat. Because as any good industrial engineer knows, continuous improvement is never truly finished. Now, here is a critical distinction you absolutely must grasp when we talk about modern Industry 4.0. There is a huge difference between a traditional simulation and a true digital twin. A traditional simulation evaluates specific scenarios in a static, isolated virtual space. It's incredibly useful, for sure, but it's disconnected. A digital twin, on the other hand, is completely dynamic. It relies on a live, two-way data exchange using IoT sensors to accurately reflect its physical counterpart in real time. It's not just showing you what could happen, it's showing you exactly what is happening on your factory floor right at this very second. And the beauty is, we can scale these digital twins to match whatever we need. We can start at the micro level with component twins. Think of modeling a single valve in a giant pipeline. Then we scale up to asset twins, which combine multiple components, like the entire drivetrain of a wind turbine. From there, we move to system twins, modeling how whole integrated assets interact with each other. And finally, we hit the macro level, process twins. These mirror entire massive workflows, full production facilities, or even global supply chains, giving us the ultimate broad-scale view of operational efficiency. If you're sitting there wondering if this is all just academic theory, it is absolutely not. The vast majority of Fortune 100 firms are heavily utilizing simulation software to drive their core business decisions. It is the gold standard in the industry. Whether we are talking about auto manufacturing, hospital emergency triage, or managing incredibly complex global supply chains, the biggest players out there rely on this exact technology to stay ahead of the curve. Which brings us to our final section, Part 5, Professional Practice. We're looking at international standards and safety. Listen, the most brilliant, mathematically perfect factory layout in the world means absolutely nothing if it fails to meet global safety compliance. The legal and ethical gravity of industrial engineering literally cannot be overstated here. As the OSHA General Duty Clause strictly dictates, employers must keep their workplaces completely free of serious recognized hazards. When we're designing workstations, we aren't just optimizing for speed or throughput. We are actively designing for human factors, deep ergonomics, and fundamental life safety. So the crucial takeaway here is that a world-class facility has to operate within a very strict framework of international codes. We're integrating OSHA for general safety, ISO 9001 for quality management, ISO 14001 for environmental sustainability, and ISO 6385 to ensure proper workplace ergonomics. This level of compliance isn't just an afterthought you tack on at the end. It has to be hard-coded into the very constraints of our linear programming and our simulation models right from day one. We have covered a tremendous amount of ground in this explainer today, all the way from the foundational math of lean to the absolute cutting-edge application of dynamic digital twins and rigid safety standards. I want to leave you with one final provocative thought to chew on when you look at your own operations. Will your next major operational decision be based on a gut hunch or a mathematically proven digital twin? The tools are literally right there waiting to eliminate the guesswork. Thank you so much for joining me for this explainer, and I really hope you walk away today totally energized and ready to apply these high-level industrial engineering principles to your own smart factory transformations.